Okay, in this presentation, I will talk about groundwater quality in nature areas, and that may sound a bit off topic for a conference about groundwater and agriculture, but as you'll see, our groundwater in nature areas is influenced by our agricultural practices. So here we go. First, I'll talk about emissions, depositions, and the policy measures that were taken to reduce emissions. Second, I'll show the effect of emission reduction policy on groundwater quality in nature areas using the results of 3 monitoring programs, and I'll focus on nitrogen, and I'll finish with the conclusions. Just a quick introduction. There are several sources which emit gases with nitrogen and also sulfur into the air. The industry, livestock, cars, transportation. Now these gases can react in the atmosphere and can be deposited elsewhere through wet deposition or dry deposition. They can be deposited in surrounding agricultural areas and in nature areas. Now in agricultural areas, the amount of nitrogen deposited through the air is just a tiny fraction compared to the nitrogen which is brought onto the land by farmers by spreading manure. But in nature areas, the amount of nitrogen deposited through rain and dry deposition can really have an impact. So when nitrogen and sulfur are deposited, it can lead to acidification, and the deposition of nitrogen leads to eutrophication. Especially sandy soils are prone to acidification because these soils contain relatively few components like clay particles which can buffer the acid. And these processes of acidification and eutrophication have all kinds of effects on ecosystems, like the increase in nitrophilic species. And these species change the amount and type of litterfall to the soil, and this again has an effect on the amount and type of organic matter in the soil, and so on. So species disappear. So where does this deposited nitrogen come from? This is the work of colleagues. The graph on the left indicates the sources of eutrophication, and the graph on the right shows sources of acidification. And when we look at eutrophication, dark blue is oxidized nitrogen, and the light blue, and the colors are good now, is reduced nitrogen. Here you can see that all nitrogen deposited, approximately 2/3, when you look at the total at the bottom, approximately 2/3 is reduced nitrogen and 1/3 is oxidized nitrogen. And on the left side of the graph, you can see the different sources. So Dutch agriculture, other sources in the Netherlands, the sea, foreign countries, and unknown. As you can see in the Netherlands, a large part of the reduced nitrogen which is deposited comes from agriculture. And this is similar for sources of acidification. Reduced nitrogen from agriculture here too is a major source. So to reduce the emission of nitrogen, measures have been taken, not just in agriculture, also in other areas, both at a national and international level. Now, examples of measures which were taken in agriculture are the improvement of feed management so that less nitrogen is excreted. And the important one is slurry injection into the soil, the installation of air scrubbers in stables, and the burning of poultry litter. So a lot of effort has been put into reducing emissions, but what's the effect? Here you can see the changes in emissions. The upper table is an overall modeled estimate for the Netherlands, combining all sources, agriculture, traffic, industry. And when you look at the upper table, you can see that the emissions of nitrous oxide and ammonia and sulfur have decreased tremendously over the past 25 years. And this is partly because of the measures that were taken. But in the case of sulfur, it is also because of sort of natural developments like the change from coal to gas as an energy source. When you look at the lower graph, it focuses on agriculture. And you can see that the application of manure to the land and the emissions from stables and from the storage of the manure are major contributors to nitrogen emissions. So emissions have decreased, and here you can see also model depositions decreased. So the question we studied was, what is the effect of emission reduction policy on rainwater and groundwater quality in nature areas? Can we see a decrease? Can we see the decrease in emissions and depositions reflected in groundwater quality? Now, we used the data of 3 monitoring programs. One program is on rainwater quality. One is on the upper meter of groundwater quality, so the leaching water in nature areas on sandy soils. And one is on, these are permanent wells where we sample groundwater at 10 and 25 meters depth in, all over the Netherlands, but we selected the wells in nature areas. First, the rainwater monitoring program. Here you can see the locations where rainwater is sampled by wet-only samplers. The monitoring program has more locations, but we didn't use the locations near the coast. Before 2000 and something, bulk collectors were used, and then they switched to wet-only samplers. So when it rains, the golden cap on top opens up and collects the water. And here you can see the results from the past 25 years. You can see the weighted annual mean concentrations of nitrogen and sulfur of all the stations in time, the black dots. And the blue is the mean value. I'm sorry, the red is the mean value. And to correct for the changes in the assembly of sampling stations, also the indexed mean concentrations were calculated. So for instance, if in 1 year one sampling station didn't work, we corrected for that so we could still calculate a trend. And as you can see, there's a clear decrease in sulfur and nitrogen concentrations in the rain. Now the second monitoring program, of which we used the results, was a program where in 150 locations in nature areas, the upper meter of groundwater was sampled. On each of these locations, 10 boreholes were made to sample the upper groundwater, the leaching water, and these 10 samples of a location were mixed and analyzed. And these are all sandy soils because those soils are more sensitive to acidification and eutrophication. So these are the results of groundwater quality in the upper meter. The black dots in the figures are the individual concentrations of each location. And the black line follows the mean, and the blue is the median of all 150 locations. Some individual values are so large that they are outside the graph. As you can see, the median concentrations of sulfate and nitrate decrease over time in the upper groundwater. And this is in agreement with the decrease we saw in deposition and in rainwater concentrations. It's the same for aluminum. We can see the blue median line decreasing, and we can see an increase in pH of the upper groundwater. And here you can see a table with the decrease in the median concentration in 2014 compared to the level in 1989, so in a 25-year period. So we have less nitrate and sulfate in the upper groundwater, less hydrogen, and you can also see an increase in the sum of cations minus anions. And we also did a paired t-test, which compares for each location the concentration in 2014 compared to 1989. And we found that nitrogen, sulfur, and aluminum are significantly lower in 2014 compared to 89, and the pH is significantly higher. So when you calculate the differences between the nitrate concentrations measured in 2014 minus the nitrate concentrations in the same location in 89, and you sort all these differences, all those 150 differences, you get this graph. And you can see that around 80% of the locations had a lower nitrate concentration in 2014 compared to 89, but there is some variation. So here's a map of the Netherlands. So not all locations have a decrease in nitrate and sulfate. The green stands for a decrease, and the red and purple for increases. So you can see there's a lot of variability. And we looked at the specific nature areas, and very often the purple dots, especially in the southeast of the Netherlands, were near intensive animal housing farms. So this may explain some of the increases. So the third monitoring program we used was that we got data from permanent groundwater wells. And we selected the ones in nature areas on sandy soils. And groundwater was sampled annually at 10 meters depth. Here you can see the results. When you look at nitrogen, you can see a little bit of a parabole because you look at groundwater, which is approximately 10 years old. So the peak in nitrogen concentration is not in the early 90s, but more around 2000. And you can see an increase and then a decrease. But I do have to mention that at the same time, the median nitrate concentration at 10 meters depth is often around the detection limit. For aluminum, the mean value is higher than the 75 percentile. So the mean aluminum concentrations are depicted by, they have a few wells having outlying concentrations, so you can't really speak of a trend at 10 meters. Now, when we compare the nitrate concentrations of the rain monitoring program, and we compare it to the upper groundwater, the results are quite remarkable. In the upper groundwater, the decrease in nitrogen is larger than what can be expected based on the decrease of nitrogen in rainwater. And for sulfur, the reverse is the case. And for nitrogen, there are several possible explanations. One is that many of the locations of the monitoring program are in nature areas which are close to agricultural land. And because there is a strong decrease in sulfur deposition, there can also be a decrease in the co-deposition of nitrogen and sulfur. So apart from the overall decrease in nitrogen deposition, there could be an additional decrease in nitrogen deposition locally close to agricultural areas. The second possible explanation for this is that maybe more nitrate was taken up by the plants and less was leached, because we see an increase in the Netherlands in summer rains, and this leads to an increase in plant growth. By the way, now it's very wet in the Netherlands. So this is supported by the increase in annual evapotranspiration we see in the Netherlands. Now for sulfur, the reverse is the case. There is a smaller decrease in sulfate concentrations in the upper groundwater than can be expected based on the rainwater concentration. But here we think sulfur is released from the soil, and this contributes to a relatively higher concentration in the groundwater. So, conclusions. Sulfur, nitrogen in rainwater and upper groundwater decreased. In deeper groundwater decreased, and aluminum and heavy metals, I'm sorry I didn't show the graphs, but I wanted to keep it to the time, in upper groundwater also decreased. So less deposition is reflected in a better groundwater quality. And these are the final conclusions. Emission reduction policy works. There is less acidification in rainwater and the upper groundwater. And another important one is long-term monitoring is necessary to indicate the effect of policy measures. And the third is that other research shows that despite these positive developments, ecosystems have not yet recovered from acidifying and eutrophying effects of air pollution. So we see an improvement in the abiotic parameters, but often biota are sort of lacking behind. Some are coming back, like some diatoms, and so there are species coming back, but a lot of them still suffer from too much nitrogen deposition. Thank you very much.
Thank you, Esther, for keeping so nice in time. We have enough time for questions. I see. Oh, first, please.
And did you see any seasonal variation of the nitrate level in the shallow wells? And how often did you sample it? Annually or seasonally or monthly? Thank you. For the shallow wells.
The shallow groundwater, we only sampled 6 times in a period of 25 years. So we didn't sample monthly or annually, but more like once every 4 years or so, depending on, yeah.
Also a question about your well. So when you say you sampled at a depth of 1 meter and 10 meters, is that regardless of where the groundwater table was at the time? And the other question, are those wells paired so that you have a well cluster at a 1 meter interval and a 10 meter interval?
Okay, I'm sorry, maybe I wasn't clear on this, but the sampling of the upper groundwater, of the leaching water, was not with permanent wells. That was only the 10 meter depth. And so there were temporary wells created by drilling boreholes. And so this was only, we were only capable to do this when the groundwater was within 5 to 6 meters. So to be really correct, I should say that this monitoring program is representative of nature areas where groundwater is within 5-6 meters depth in the Netherlands. Of course, there's also nature areas like the Hoge Veluwe where groundwater is much deeper. Does this answer your question?
Not really. So does that mean that are you talking then about the upper meter, like the meter beneath the water table at the time?
Yes.
Okay, very good. Thank you.
So with 10 meters depth also means 10 meters below the groundwater table. And 1 meter's depth is 1 meter below the groundwater table.
Yes. Thanks. You gave some examples of the mitigation strategies that were being used. How much of the reduction you're seeing in the nitrogen and sulfur and other emissions are due to the fact that, as I understand it, the Netherlands is exporting a lot of its beef feedlot excreta to other parts of Europe, I think particularly into eastern parts of Germany. And shouldn't that be in the balance sheet?
I don't know exactly. The emission registration is done by my colleagues. So if this is, I don't know if this is taken into account or not. But if you want, I can come back on that later.